Okay, ladies and gentlemen, looks like we do have our audio. Good morning to all of you. I hope you're well. All right, let's see what's going on here and see what I sent everybody. So you guys remember here, I sent you guys a few things. Well, you have, let's go to the assignment section. You have test 4. See if you guys are aware, right? Your test 4 is a take-home test. Is that right? And it is here. When is it due? It's in the assignment portion of Canvas. So when is it due? Do you guys know? Thursday, the day of your final. What time? 8 a.m. In the same manner that you guys have always done things. Turned it in. You use the Cam Scanner Plus, yada, yada, yada. So you guys turn that in. So, and it is a test. You're supposed to work on it by yourself, right? Don't go into any tutoring center. You say, hey, do my test for me. And then I also sent you guys your study guide for your final. That's on what day? Thursday as well. So I sent you guys that information here. So it's Thursday at 8 a.m. from 8 to 10. Anyway, so that's kind of what's going on. Anybody have any questions on all of that? No, you guys are aware of all those things, hopefully. All right, good. And then I'm going to go here to our hypothesis testing and our notes. Yeah, so now we're going to look at this here. Hypothesis testing here, notes. And it's going to download. I wonder here if I can do the same on the iPad. Let's see if it's going to do this. All right, so I'm going to import some of those things. Okay, I'm going to do that on the iPad. Import some notes. All right, so I did import some notes here. So let's go back to. Okay, so all right, so let's ask you guys a question here, right? You guys have done some work on some hypothesis testing, I hope. So let's transition to do some more work on hypothesis testing. It's going to be the same format, essentially, the same process procedure, but now you're going to do a hypothesis test about what parameter? What does it say here? It's now going to be about a what? About a mean. Okay? Now, I'm going to emphasize something here for you guys because we're going to have a couple of situations. We're going to start with a mean for a large sample. So a large sample is any sample size greater than 30. So this is called really hypothesis testing about a mean for a large sample, which is why you see in the notes, what it says here. Now I'm gonna leave these notes here for you. If I go back to the browser there, and to remark that hypothesis testing by mean large sample, you have a video on that, on the notes, really. You guys have a video of these notes, hypothesis testing about a mean. So, what I'm going to do, just to give you guys some variation, I'm going to do different kind of examples than what's on the notes. So even if you said, okay, I want to see what's on the notes, well, you have it here, right? You have that video. So I'm going to do a little bit different examples, whatever. Because I think sometimes people say, I prefer your language or whatever approach. So I'll be doing that. So it'll give you guys an example of what I'm talking about, right? So let's create a hypothesis test here to show you guys what I'm talking. And it has to be it's going to be about a mean. A mean is a different parameter, right? A proportion P is like a probability in a percent. So a mean is like it's just an average. So when we think about this, I might think, oh, what should we think? How about if I make a hypothesis and say the mean lifespan of an iPhone, okay, I'll say maybe is 4 years, okay? And then you should see something like this, as claimed by somebody. Well, I'll say as claimed by Best Buy. All right. So as claimed by Best Buy, the mean lifespan of a iPhone. So remember, what's a lifespan? Do you guys remember? What's a lifespan? It's just how long something lives, even though you say an iPhone does not live. And I'll tell you, you're right, an iPhone doesn't live, but you can think of it as how long it lasts. And, like we look at lifespans of objects often, lifespan of a car, lifespan of anything, of a laptop, lifespan of, any sort of physical device, because we want to know how long that thing lasts. We call that a lifespan. So in this case, it's just an iPhone. Okay. So the lifespan of an iPhone, and by the way, your warranties are based on these kind of situations, the lifespan of an iPhone. You ever notice why it breaks right when, the warranty wears out? Do you ever notice you go, oh my God, your iPhone just died or your laptop just died, and guess what? You check the warranty, just ran out. Well, because they're aware. They're aware of the lifespan, the average lifespan. So anyway, that's the deal. So we're going to create a hypothesis test as an example. The lifespan of an iPhone is 4 years as claimed by Snodgrass, right? So starting with how we looked at this before, right? What's the parameter here again? Yeah. And then how do you know they're talking about a mean? They're going to tell you. Okay. So you go, oh, okay, this is a hypothesis test now about a what? About a mean mu. So you say, okay, they're going to give me mu. Now, what about mu? What are they saying about mu? Lifespan is what? Is 4 years, right? And then you say, well, how do I know this is a hypothesis? Well, they're going to also have what? As claimed. Remember, a claim by somebody or some person, somebody's making a claim, because that's what a hypothesis is, right? So this is what they're saying, as claimed by this person. It's not even a person, it's by Best Buy. So when you translate this, what do you guys do? What does that mean? It's what's the inequality symbol for is? Equal. Good. So you're going to say mu equals 4, and I highly recommend you guys write down next to it what? Claim. All right. So you go, oh, okay. Mu is 4. Yes, it is. That's the claim. So the first major part of all of this is just translating. You go, okay, mu is 4. All right, somebody's making the claim that the mean lifespan is 4 years. Now, here's what's going to come next. If you guys notice the format of how these questions are given, really, they're going to now give you sample information, right? So they're going to say something like this. They're going to say a sample of, now what is large again? 30. So I'm going to say a sample of 50 iPhones. That's bigger than 30. Okay, so that's a large sample. So a sample of 50 iPhones reveal a mean of 4.2 years with a standard deviation of maybe 1.6 years. Okay? So they're going to even say this to you. They're going to even say, okay, here's your sample information, and you know it's a sample. You say, how do you know? Because they're going to tell you what? a sample. And then when they say a sample of 50 iPhones, what does that mean? You guys know, remember, I always like to write down the sample information. I even put it in red. And I'm going to say, what does 50 mean? That's your sample size. Is that true? And yes, that's large. So I'm going to say, okay, that's a large sample. Bigger than 30. And then what else do they tell you? Well, they have a mean. Now, that's a mean that comes from a what? From a sample. So if they have a mean that comes from a sample, then that's a sample mean. Does that make some sense? And what's that value? 4.2. And then they say it has a standard deviation as well of 1.6 years. So you're going to put S equals what? 1.6. So this is, the first kind of hypothesis testing question you have for a mean now, large sample. What's the last piece of information they're going to give you? What are they going to say? They're going to say use the what? 10% level of what? Significance to test this claim. Now, we're going to talk a little bit later about the meaning of this, so I'm going to put this, I think I usually don't remember. Let's use gold. Okay, so you say we got this level of significance information. It's the complement of the confidence interval, but okay. We're going to talk a little bit about that specifically, not right now. But anyway, this is alpha equals what? 10%. Okay, you guys okay with that? So everything is already given to us in a typical question here. And I'm going to use my own, language questions for some of these. And this is a hypothesis test about a large sample. All righty. Okay. So do you guys remember the procedure that you did for a hypothesis test about a proportion? What's the first thing that you do always in these tests? What's the first thing you guys do? That first step. You set up your what? Hypotheses. Good. So in other words, you have this H naught. You have this H1. So this is your hypothesis setup. You set it up. So what does that even mean? Where do you put this? You guys remember? You already know what the claim is. What do you have to know about this claim? Where does it belong? Is it a null or is it an alternate? Right? Is it a null or an alternate? It's a null. It's a null. How do you guys know it's a null? The condition of what? Equality. Anything with a condition of equality is a null hypothesis. Good. Okay. So what's the opposite of that statement? Not equal. So now you say, okay, mu is not equal here to 4. So either mu is going to equal 4 or mu is going to not equal 4. Okay, you guys okay with this? Easy peasy? All right, well, let's see. What comes next? You guys know what comes next after you set up your hypothesis? You set this up. Your hypothesis is set up. You even labeled the claim as mu is 4 because that's the claim. So, okay, what do you do now? What do you have to do? What's the next step in the process always? You got to create your what? Decision rule. So you're going to use your normal distribution here because it's based on the central limit theorem, right? This is all based on that central limit theorem. Sampling distribution of the means. But we're going to use that standard normal Z distribution. How many tails is your test? What kind of test is this? How do you know it's a two-tail test? Because you always look at the alternate hypothesis, and when it is not equal, that means you have a what? A two-tail test. Not equal is a two-tailed test. All right, so we're going to draw two tails. So make sure you draw two tails. And what do you label that middle region here that's not shaded? Do you guys remember? What do you label that? Do not what? Do not reject your null. And then what do you label the shaded regions? You're going to reject your null. Now, what goes down here? Yes, you guys have to put your critical values. Good. So we need those things called critical values because this is a decision rule, right? You got to know if your test statistic lives between these two numbers, these critical values, you got to know what those numbers are. Now, how do you find that out? You got to go back to the what? Your level of what? Significance, 10%. Now, if there's two tails, what does that mean? If alpha is 10%, that means what? 5% is in each what? Tail, is that right? 5% is in each tail. So you're going to need to use a special function. What was it? Let's wake up the calculator. Do you guys remember? How do you get critical values for the Z distribution? You're going to have to use the what? Inverse norm. Okay, so I'm going to wake up the TI here, okay? So, okay, TI, wake up. And then we go, okay, here we go. TI, second distribution, the inverse norm. Do you guys see where it is? Oh, it's number 3 here. Okay, number 3. Now, I'm going to put 5%. 0.05 is 5%. Because this is a Z distribution, mu is 0, sigma is 1. That means 5% is in my what? Left tail. Is that true? So take a look at your picture. What I'm saying is 5% is in that left tail. Alpha's 10%, half is in each. So that's what I'm going to paste in the TI. So now we hit enter, and sure enough, what's this number to the nearest thousands? Do you guys know what is that to the nearest thousands? Negative 1.64 what? 5. Okay. So this is that left critical value. However, we have two. We have one on the left, one on the right. So the other one is a positive 1.645. We're using symmetry. So ladies and gentlemen, there you guys go. You have your decision rule here. You guys can see these things in red are the critical values. There are 2 critical values. 2 of them. Okay? And so you're now ready to do what? What comes next? Step 1, set up your hypothesis. Step 2, create your decision rule. Step 3, take your what? Sample. We already did. Your sample's right here. Step 4, what happens after you take the sample? Right? What happens after? You have to now compute the what? Test statistic. So you might say, how in the world do you compute the test statistics? This is a different parameter. Well, let's look at our notes. Right? We're doing hypothesis about a large sample. Let's see what the notes say. Inverse norm. Okay. So this is what you guys need to do. Let me see. Okay, so I have the notes even in the iPad. So what's in the TI, what's new for us? We got to go to what? Stat. What else? Test. What else? Z-test, ladies and gentlemen. Oh, we can't see anything. So we're going to stat, test, Z-test in the notes. Now, we're going to need to know some information, and you're going to go back and take a look. We need something called mu naught, though. Right? What do you think mu naught is? What was P naught? If you guys worked on that homework, what was P naught? P naught was the proportion in the null hypothesis. So what is mu naught? The same thing. It's the proportion in the what? Not proportion, but it's the what? The mean in the null hypothesis. Let me go back and find what I'm looking for. So you say, what's that going to be, or mu naught? It's going to be 4. The mean in the null hypothesis is mu naught. And what was the name of that test in the TI? All right. So in the TI, Z-test now. And I'm going to write down in green, mu naught equals what? 4. So we have all the information we need to compute our test statistic. Everything we need. Okay. So let's see if I can do this. You say, what are we going to do? We're going to go to what? Stat, test. You know what Z-test is? The first one. Right? Z-test. So go down to mu naught. What's the value of mu naught? 4. Now, really, technically, ladies and gentlemen, I have to remark about this stuff. I know you see the symbol sigma. Now, sigma is a population parameter. In all honesty, yeah, you'd use sigma. If sigma's known, you would use this. But sigma's not really known necessarily. So we're going to use the sample what? Version. So what was the sample version here? 1.6. Okay. What's the sample mean? 4.2. What's the sample size? Oh, they must have known we were looking for 50. Now, which one do we use here? What does this say here? What is this? This is what? Mu not equal to mu naught. You're looking at the statement. That's the alternate hypothesis, right? It's a two-tailed test. Remember the alternate hypothesis inequality? So this is a not equal. We're going to make sure it's on not equal. This tells the calculator this is a two-tailed test. We're now ready to calculate. So hit calculate. Now, what do you think your test statistic is? It's going to be the what? The Z value, the second value there, which is point what? 8 what? Let's go to the nearest what? Thousandths? 8 what number? 4. Do you guys see that there? And then what do you guys see below that? There's a P. Give me that P also to the nearest thousandths. 0.37 what? 7. Is that true? Because I'm going to talk a little bit later about that number as well. Anybody know what that is? By any chance? You guys happen to know maybe? Maybe not. Okay. So I wrote down the Z value. That's my test statistic. That's what we're going to use. I put down this P value as well and call it P value. I'm going to talk about it a little later. Just got to notate it now, but we'll talk about it later. And I'm going to put this in a highlighter. Okay. I'm going to even say, okay. I'm going to highlight this so I can remember how to find it really easily. And so now, ladies and gentlemen, where does that Z value test statistic live on your decision rule? Do you guys know where it lives? 0.88 is, first of all, it's positive. Is that right? But is it past your critical value? No, it's like kind of maybe over here. This is where that test statistic of 0.88, what is that? 884 would be. So it's not, it's positive, but it isn't past the critical value. Now, remember what this means here. Think about this. The test statistic lives between the critical values. More importantly, it lives in the what? Do not reject the null. Okay? So I'm going to say something here to you guys. I'm going to put this in red here. What does it mean to not reject? They should have just said, in my opinion, they should have just said to accept the null. Is that true? Not rejecting is like accepting. So you go, okay, we're going to accept the what? The null. So if you're going to accept the null, embrace it. You're going to hug it. You're accepting it. You guys know what I mean? You accepted the null. So you're hugging the null. What does that mean, though, about the claim? What does the claim happen to be? Because there's really two questions here. The rigidity of this test is simply saying, hey, accept the null, do not reject it. And you go back to the null, you happen to see that the null is exactly what is the claim. Is that true? So since the null is the claim, ladies and gentlemen, what's your real conclusion here? What's the conclusion? What do you say in conclusion? The sample supports the claim. Because, ladies and gentlemen, there's really only two conclusions. So here, the sample what? Supports the claim. So you just support, your sample supports the claim. The claim is that the mean lifespan of an iPhone is, in fact, what? 4 years. So that's what we're doing, ladies and gentlemen. That's how this all works. Is that easy peasy lemon squeezy? So all that's new for you is a test statistic, is the z-test. And it works very similar to the t-test, I guess. No, I'm sorry. What was the other one? One proportion. What was the other one? Let's go back. I don't even remember. I got to go. Let's see. Did you guys do any homework? I hope. Because don't blink. What happens if you blink? So what was your homework on? One proportion z-test. They should have called this one mean z-test. That would be consistent. Is that right? But they didn't. It's z-test. All right. What do you guys think about this hypothesis test about a mean? Isn't that just very similar? Exactly. So that's the beauty of it. These things are very similar, these processes. So you're testing a hypothesis about a mean. So I always like to give that first example of an equal. The next example I like to give as a hypothesis test is a not equal, because I want to give you guys some language, right? So what do you guys care about as college students in terms of a mean? What do you care about? What do you guys think? What do you care about? College students. You guys don't care about anything? How about this? Maybe I shouldn't always ask, because people care about the same things all the time. Did you guys get any sleep last night? A little bit? How about this? The mean hours of sleep college students get is not 8 hours. Sorry. Okay? A sample of 120 college students reveal a mean of, okay, let's see, you guys, let's see. How about this? 7.2 hours with a standard deviation of 2.5 hours. Use the 1% level of significance to test this claim. Okay. So we read through this because that's going to be important. You got to know, okay, what are they asking me? The mean what? Hours of sleep Culturans get is not what? 8 hours. Oh, I forgot to put, let me go, I'm gonna forgot an important statement I always put. What do you think I have to put? As claimed by who? Snodgrass. Good old Snodgrass. All right. So as claimed by Snodgrass. So I want to point that out to you guys. This is a what? This is a claim, okay? A claim is a hypothesis. So mu is not what? 8. That is going to be the what? The claim. Do you guys agree with that? Mu is not 8. That's your claim? So when you set up the hypothesis, where does that go? Is that a null hypothesis or is that an alternate? So put it in the alternate position. What's the logical opposite of that? All right, you guys okay with that? Mu equals 8. So what do you guys do with this now? What do you guys think? Tell me, what kind of test is this? It's a two-tail test. So you're going to put 2 tails. Here, where else? Here. So in the middle, you say what? Do not reject the null. The tails, you what? Reject your null. So I know that they gave me a sample. They're saying 120 college students have a mean of 7.2 hours, standard deviation of 2.5 hours. So I do know all that information. So I know my sample is large. Remember, I need to get some critical values. There's going to be 2. So how do you get the critical values again? Do you guys remember? You go to what? Second distribution, inverse norm. Isn't inverse norm number 3? Okay, but you need the level of significance, don't you? So I have to read further, and they're going to tell me use the what? 1% level of significance. Okay. So my alpha is what? 1%. So let me write this down here for you guys, okay? 1%. How do you guys write that as a decimal, by the way? It's like a penny, is that right? Good job. Look at that. Like a penny. You got a penny there? 0.01. How do you take, what's a half a penny? Do you guys know? If you don't know, do the following, right? Say second quit 0.01 divided by 2. What is this? Is it 0.00 what? 5? Oops, sorry. So it's 0.005. Why is that an important thing to know? Because when you try to find those critical values, they go here and here. Okay, go back to that inverse norm. So it's second distribution, inverse norm, 0.005. Mu is still 0, sigma is 1. It's still on the left. Do what? Paste that. What do you end up with? What is this number to the nearest thousandths? Yeah, what is it? Negative 2 point what? 576. So that's in the left. There's 2. I'm going to get rid of all of that. So now I have my 2.576. I got my 2 critical values. Ladies and gentlemen, there it is. So here's your 2 critical values. What do you guys think? Did you guys work on that? Hopefully, right? Okay, now, what comes next? You say, okay, take your sample. Well, we did take a sample. What's the sample size again? You guys remember? 120. Okay. What's the sample mean? What was it? 7.2. Good. What's your sample standard deviation? Okay, what was mu naught? You go, uh-oh. Mu naught. What is mu naught again? It is the what? The mean and the null hypothesis. Mu naught, it's right here. So mu naught is 8. Is that right? So I'm going to write that down even in green here. Because in the TI, we have to use z-test. You know, I might even write that down. Like if I was doing my homework, I'd write that down even in the TI z-test. Because this is kind of like training yourself to get the right answer. Just writing down all the important information you guys need to use the calculator, right? All right, so let's go to the TI. You go second distribution, not second distribution, I'm sorry. Stat what? Test, it's the first one. It is what? The z-test. Okay, now, ladies and gentlemen, go down over here. Mu naught is 8. Yes, that's That's going to be S. I know it's sigma, 2.5. And then we have the sample mean is what? 7.2. Sample size now is 120, ladies and gentlemen. And then, is this a two-tailed test? Okay. Now hit what? Calculate. Okay. What is Z to the nearest thousandths? Negative 3.505. I'm going to go and I'm going to write down the P. Yeah, the P. It's called the p-value, by the way. We're going to talk about the p-value. What's the p-value here? Yeah, I'm going to do this here. So notice it's in scientific notation. 5596. It's actually 97. E to the minus 4. I'm just going to write that stuff down here like this so you guys can see what I just did. Okay, we're going to talk about this stuff. Just going to notate it now. Okay, so here's my test statistic. This thing is called a p-value. We don't know what it is, but we'll talk about it. And I'm going to highlight this because I want to get back to it. So the test statistic of negative 3.505, first of all, it's negative, so it's to the left. But is it past your critical value to the left? What do you guys think? Is negative 3.505 past? Yes. It's like somewhere maybe over here, right? Negative 3.505. That's where the test statistic is. More importantly, what neighborhood is this in? Anything to the left of that critical value, like a negative 3.505. See this here? Anything to the left of this critical value, what do? We reject the what? The null. So you guys are looking at an important idea. You're rejecting what? The null. So when you reject the null, remember this. You go back to your hypothesis and you say, what? Okay, null. You are rejected. You're gone. So you got rid of the null. The null is what? Gone. So if you're getting rid of the null, what are you actually accepting? The alternate, which happens to be your what? I'm trying to hug the alternate. But it doesn't, whatever. Here we go. You rejected the null and you're hugging the alternate, which happens to be your what? Claim. What's the conclusion? What are you guys going to say? Sample supports the claim. And you're what? Done here. The sample supports your claim. So, ladies and gentlemen, pretty good deal. All right, you guys okay with that one? What do you think? Is that okay? Easy peasy lemon squeezy? All right, how about this here? So should we have you guys try one on your own? Just to check? Try a couple maybe? I don't know. What is this? Oh, whatever. Sometimes I hope those 4 people at home. Yeah, it's supposed to be here. Says that it said supposedly what the internet connection in the basement here is what? Bad. Yeah, it is bad. Oh well. Well, they have a video there. Like, man, they got a backup video. What do you guys think? Man, I don't know about you guys. It's always good to have a backup plan. Did anybody think of that way? You got to have a backup plan. You got plan A, plan B, plan C. All right. Let's think about a mean. Oh, I'm gonna think. What do you guys care about? You care about sleep? Where are the people on Instagram again? What do you guys have on Instagram? You guys care about Instagram or you guys care about TikTok? Neither? Facebook. MySpace. You guys are probably born after MySpace. Did they have any friends in MySpace? Do you guys remember? I don't remember. No? Anybody here have a MySpace? Does your grandma have MySpace? You say, Mr. Judge, my grandma's the only one I know who has a MySpace. Right? Is it that old, MySpace? Yeah. The mean friends on Instagram is more than what? What do you guys think? I don't know. Is more than 200 as claimed by who? Elon Musk. Maybe he wants to buy Instagram as well. A sample of 500 account holders reveal a mean of, I don't know, is 200 a lot of friends? Anybody here have more than 200? Just curious. I don't know. What do you guys think? Is 200 a lot? Oh, I don't know. Is Instagram have followers or friends? Whatever. I messed up. Sorry. Let's pretend they're friends. Who has friends? Is it on Facebook? Is that your? Facebook has friends. Should we change it then? So it's consistent? Because that's a little, I don't know about you guys. I hate that. So if, we'll say Facebook. Right? You guys could get depressed, though, if you're on social media. Which is the most depressing social media platform? Instagram, you think? Why is that? You're just scrolling? I don't know what it is. Isn't that a weird platform? Yeah, I had. I'm like I said, I'm like a lobbyist, for a faculty association, and they asked me about. So I had to get on Twitter, and I gotta say I hate it. So even though I'm on it, I'm not really on it. It's like a mean platform. It's like a place you go to be mean. Now I could be mean, but I don't really want to. I don't want to live to be mean. Like if you look at something mean right before you go to bed, what happens? You stay up. At least I do. I'm like, oh my God, I can't believe that. So I'm like, forget this. X, Twitter, whatever. So even though I'm on there, I'm not really on there. Sorry about that. What would I tweet about anyway? That anybody even cares? Nobody cares. I could retweet? I don't even know what retweeting really is. It's just tweet a tweet. I'm going to have you help me learn how to do that because I don't even know. Yeah, I don't know. You know what I did? Yeah, it's not even broadcast over the internet, so I can tell you guys. Did you guys know? Who's the best baseball player besides Mookie Betts and Freddie Freeman? Whoever lived. Do you guys know? You say I don't even like baseball. Who likes baseball? Good. Who was the top free agent in this last off season? See if you guys know. See if you know. The top free agent. Huh? Oh, that's Summer. No, Summer. Who was the top free agent? Do you guys know? You guys probably don't even know. You don't even care. A guy by the name of Aaron Judge. Does that name sound familiar? Aaron Judge. Do you guys know? You want to know who Mr. Judge is related to? Aaron Judge. You ain't gonna believe me. Now, I grew up in East LA, but Aaron Judge didn't, and I know if you tell these stories, you could get beat up. Right? You get beat up if you start telling these stories. Because people don't want you to lie. You get beaten up. At least in my day, that's how it worked. So if you're around telling everybody you're related to Aaron Judge, it better be true, otherwise you get beat up. But it's actually true. He doesn't know it. I know it. And I tried contacting him. You know what? He ignores me. Tried contacting him on like Twitter or something. I even have my daughter. Hey, Aaron. You know, our fathers are cousins. So he doesn't know it. I was going to have him try to come down to ELAC. Say hello or something. You know what I mean? When they played the Angels. So why don't you stop by ELAC before you go to the stadium? Yeah, he's not listening though. Anyway, what am I telling you guys about this? Oh, I try to do it on social media. Try to contact them. What if I go to an Angel game and start yelling as a crazy fan? Hey, Judge! Yeah, I don't know. I don't think it's like if you got $300 million and all your relatives came out of the woodwork, would you respond?
I wouldn't tell anyone if I won the lottery. I would tell like only my immediate.
Not lottery, but like him. Like if I was him, I'm just putting myself in his position. Like how many relatives are coming? You know, I can kind of understand why he doesn't respond. It's like he's gonna want some money. I mean, he's just too busy. He's too busy to care. Did I take a DNA test? I don't think he would say, take a DNA test to prove it. I don't think he'd really care. He'd be like, hey, what's up? That's it. No? Would you care? You would? Good. No? See, you wouldn't care either. Yeah, whatever. Aaron Judge. He's adopted, by the way. So the genetics aren't there. Yeah, he's adopted. Yeah, our fathers are cousins. But my father passed away, so I can't tell my dad, hey, Dad, hook this up. Can't. My father's passed away. It's like, oh, man. I remember him talking about him when, years ago. Anyway, whatever. I guess that's not going to ever happen. Sample of 500 account holders reveal a mean of how many? How many friends on Facebook? I don't know, maybe 222. Standard deviation of 38.2. Let's say 0.5 because, you don't have a whole number mean necessarily. Use the 5% level of what? Significance to do what? Test this claim. So I'll give you guys some time, and maybe I will do a sign one day and go to an Angel game. Try this out. All right, ladies and gentlemen, let's take a look at this, right? Let's read this. What does it say? The mean what? And it should be, I would say here, I would edit this and say the mean number of friends, right? Excuse me. The mean number of friends on Facebook is, what's this? More than 200. As claimed by who? Elon Musk. So this is mu. Thinking about the claim. So what is this? Mu what? More than what? 200. And then that is the what? Claim. So we have what? H naught, H1, and mu more than 200. Where does that go? Is that a null or is that an alternate? No, that's an alternate. You guys okay with that? Good. Now, what's the logical opposite? Mu less than or equal to what? 200. Okay. So, ladies and gentlemen, we just set up the hypothesis just by reading that first statement. And then let's read the rest. It says what? A sample of what? 500 account holders reveal a mean of 222.5 with a standard deviation of 38.2. Use the what? 5% level of significance to test the claim. So what I would do now at this point is, since I have more information, right? You're gonna do the following. You're gonna do what comes next, which is always to create your decision rule. However, when you create this decision rule, we have to know what kind of test this is. So what kind of test is this, by the way? Right? You always look at the what? Alternate hypothesis inequality. That is pointing in what direction? Isn't that pointing to the right? Okay. Since it's pointing to the right, this is a what? A right tail test. So draw a right tail. Now, the non-shaded region, we call that the what? Do not what? We do not reject the null. And then what do you say about the tail region? We do what? Reject the null. So what's your level of significance? What's alpha? Since alpha is what? 5%. 5% is in that right tail. So we need the critical value. Alpha is what? 5%. So take a look at all that, ladies and gentlemen. What do you think? Is that okay? All right. So let's go now and look for inverse what? Inverse norm, second distribution inverse norm. And that's not 5%. So I'm going to put 0.05. Mu is still 0. Sigma is 1. That's the standard normal distribution. I'm going to use the right tail now. I'm going to use that right tail. What do you guys think? Right tail? Isn't that what you guys are seeing right here? A right tail? And that's 5%. So I'm grateful for that version of the TI. Okay. So paste that in. And what is this? What is the critical value? 1.645. So to the nearest thousands, it is 1.645. Okay. So good. We got the critical value. So this is our decision rule. So we already have the what? We have the setting up of the hypothesis. You have the decision rule now. Okay, you guys okay with that? Good. And now you say, what comes next? That third step is to take a sample, but you don't really take a sample. You just read the sample information. We need the sample size, the sample mean, and the sample standard deviation. So when we go back and read that, what's the sample size? What does it say? You have a sample of what? 500 reveals you have a mean of, well, that's a mean from a sample, 22.5 with a standard deviation of 38.2. So 500, 222.5, and what was the standard deviation? 38.2. Okay? So you got the sample information. All right. Now remember what I'm going to paint this green. Why am I looking at this? Right? Isn't that the mean from the null hypothesis? Isn't that mu naught? I'm going to need that because in the TI, I believe it's z-test, we need this information, and we're going to get the test statistic. We're going to get that p-value as well. All right, so we're good to go. Let's go to the TI, and we're going to say stat test. I think there it is, z-test. Okay, go down now and say, what's our mu naught? 200. Standard deviation, 38.2. Okay. Sample mean, 222.5. Okay. What's the sample size? 500. What kind of test is this? A right tail. Hit equal there, right tail. Okay. And then what's the deal? Calculate. Oops. It should be there. I hit it twice, but oh, sorry. This is all the information we had. Hit calculate. Make sure it's on a right tail test. So what's the z-value approximately, ladies and gentlemen, to the thousands again? Isn't that 13 point what? 1, 7. What's that p-value below, by the way? 6 point, what is that? 729, but don't forget the e to the minus 40, ladies and gentlemen, okay? So I'm going to write this down now. We're going to talk about it. So let me highlight the test statistic. Let me highlight this thing called the what? What do we call that, by the way? P-value. And I'm going to highlight this again because we're going to go back and we're going to need this. All right. So a test statistic of 13, is that test statistic beyond the critical value of 1.645? I would say it's really beyond. Is that right? 13 point whatever out here. This is that. I'm just going to say test statistic. This is very much in the what? What region is that test statistic living in? Anything to the right of your critical value, you reject the null. This is in the rejecting of the null region. Does everybody agree with that? With the test statistic value being 13.171, you reject the null. It's past the critical value. So what does rejecting the null actually mean again? Do you guys remember? Goodbye, null. So if I said goodbye to the null, what does that mean about the claim? The claim is an alternate hypothesis. So what's our conclusion? Do you guys remember? What does this mean here? Let's find a place to put our conclusion. This means the what? The sample supports the claim. And there you go. Sample supports the claim. So, ladies and gentlemen, pretty good. All right. Should we try one more just for fun? Let's see. How about this? Is the internet still down? Yeah. It's like no internet on campus. How about, what do we want to think about? The mean what? The mean lifespan of a router? No. We don't want an IT question, do we? No IT questions. The mean lifespan of a router. How about this? The mean age of college students is at least 22 years, as claimed by Snodgrass. Okay, and now we're going to say here, a sample of 150 college students reveals a mean of, or I should say a mean age of, 20.8 with a standard deviation of 1.2. And of course, these are years. Okay? Running out of space there. Use the, what do we use in the past there? It's 5%. I'm going to say again, use the 1% level of significance to test this what? Claim. So I'll give you guys a few seconds to write this down. Okay, let's go through this one. Okay, you guys ready? What does it say again? The mean lifespan, I'm sorry, not lifespan, the mean what? The mean age of college students is what? Is at least what? 22 years as claimed by Snodgrass. So you're going to put mu. We're going to put mu is what? Greater than or equal to 22, and then you have what here? This is the claim. So the mean age of college students is at least 22 years. Now, H0, H1, where does that go? Is that a null or is that an alternate? Okay. How about this? That's a null because of the condition of equality. So what's the opposite of the statement? Mu is less than 22. Okay, so far so good? All right. So if we read this, use the 1% level of significance. What does that mean about your alpha? Alpha is what? 1%. So with our decision rule, again, what are you guys going to do with this? You're going to move this down. So you guys want to tell me, what kind of test is this? Right. That's what kind of test? It's a left tail test. Good. So your inequality is pointing to the what? To the left. This is a left tail test. So this means we have this. This is our reject the null region. This is the do not reject the null. %1 is in that tail here. So maybe we should use the same color. Alpha is 1%, so 0.01. Again, we're going to need a critical value to go right here. Again, this is that Z distribution. 0. Z. Okay. Second distribution, inverse norm. So make sure that's on 1%, and you go to the what? Left tail. What is this value to the nearest? Negative 2.3 what? 3 point, what is this to the nearest thousands? Negative 2.326. Okay. So you guys have your critical value. Easy peasy lemon squeezy. There's your decision rule. So let's get our sample. You guys ready for the sample? What does that say? We're going to need a sample size, a sample mean, and a sample standard deviation. What's the sample size? 150. N has a mean of what? 20.8. Standard deviation 1.2. So 150, 20.8, and 1.2. Now I'm going to get this green. I need a mu naught, right? Remember, in the TI, we need a mu naught, meaning we need the mean in the null hypothesis. And that's going to be what? 22. In the TI, we use what? Z what? Test. We're going to need the Z value and that thing called a P value. Okay? All right, we're going to need the Z value and a P value. So, ladies and gentlemen, let's go to that TI and punch everything in. Okay, so we're going to go to stat test, Z test, the first one. So mu naught is 22. Standard deviation, 1.2. Sample mean, 20.8. Okay. What's your sample size? 150. What kind of test is this? A left tail test? So put this on the what? Left tail. That's a left tail test. Left tail. Okay, remember, this is a what? Left tail test. And you should see a left tail. All right. So what's that Z value going to be here? Negative 12 point what? 247. And then the p-value equals what? 0. We're writing that p-value down now. P-value equals 0. Okay. So let's look at this here. That test statistic is negative 12. Isn't that to the left of that negative 2.3, the negative 2.326? So your test statistic, ladies and gentlemen, is like really off the iPad. It is certainly to the left. Okay. It is to the left of your critical value. It is off the charts to the left, right? Your test statistic, negative 12, way out here. 12 point what? 247. So what neighborhood? It's in the reject the what? You're going to reject the null because your test statistic is really far to the left of the critical value. So rejecting the null means to do what? Yeah, you're embracing the alternate now. You're hugging the alternate. So you rejected the null only to hug the alternate. Now, the alternate hypothesis is saying that the mean age of college students is less than 22. That is not your claim. So the sample did what to the claim? Does not support. So the sample does not support your claim. And that's what happened with the sample. It does not support this claim. So it's suggesting, the sample suggests that the mean age is actually under what? 22. And that could kind of make some sense because the sample means like 20.8, and how consistent that is 1.2, and that's a lot of data values, 150. So, ladies and gentlemen, this is an illustration of the z-test and the TI. Now, remember, we've been actually mentioning this thing called a what? This thing called a p-value. Okay? So what I'm going to do now here, and then hopefully people at home, I guess is the internet still down? It sure is. School. Wonder how long it'll be down. Well, we're here, and I am glad, ladies and gentlemen, I downloaded the notes, because what I would share with you guys here, maybe if I went back, let's see if it's in the cache. Right? Remember this thing here? Let's go to this p-value. No, sorry. P-value notes. Well, it's in my iPad because I downloaded it before the internet went down. All right. So in the website, on the notes there, under hypothesis testing, let's talk about this idea called the what? That p-value. Okay? The p-value that your TI has been reporting, does anybody know anything about this p-value? All right, let's talk about what the p-value is. Maybe you already knew. So here's kind of the idea. It's known as the modern method for hypothesis testing. And a lot of times in hypothesis testing, you're going to hear a lot of things about the p-value. Okay? A lot of things about this p-value. So what we've been working on is the traditional method, not the p-value or modern method. So the p-value modern method is to say this to you. Our entire analysis can be boiled down to one number called the what? P-value. So in other words, taking a sample, computing a test statistic, this all could be boiled down to this number called that p-value. And if the value, is less than the level of significance, we've been calling that alpha. Okay? Because what you want to know is how small really is the p-value. So a lot of times you say, okay, Mr. Judge, what is this? We're going to see what this is. But you compute that p-value, and you really want to know for that number how small it is. Now, remember probability values that are like less than 5%? What did that mean if a probability value was less than 5%? So go back to that kind of discussion, right? So you had before, if P was less than 5% for a probability, what did you say about the event? The event was not likely. Remember that? So you can say that the event is not likely for a P or a probability to be smaller than 5%. That's what a p-value actually is. It's a probability value. So you go, oh my God, a p probability, that makes some sense. Yeah. So, we already know if a probability is under 5%, the event is not likely. All right. So that's a pretty small probability value. So that's kind of what we're concerned with, right? So if you said, okay, what does this have to do with, what we're looking at in terms of a hypothesis test, right? So if your p-value is less than the level of significance, remember, sometimes alpha is 5%. Remember how we've been saying, alpha being what? 5%. So if that p-value is less than the alpha value here, okay, that is what we're going to be concerned with. Well, that means it's small. And if it's smaller than 5%, an event is not likely. So let's continue to read. If your p-value is less than the level of significance alpha, then we can say we have found statistical evidence in favor of the what? Alternate hypothesis. Now, remember, here's what this is based on. This is based on the assumption your null hypothesis is valid. Okay? So we assume the null hypothesis is what? Valid. That's an assumption. However, P is the probability that the null hypothesis is valid. So if you go, okay, P, probability your null hypothesis is valid. What happens if it's low? If it's low, then the null has got to what? Go. And you say, why? Okay, you see this P? If P is smaller than that 5%, it's not likely the null hypothesis is valid. So what we say, if P is low, the null has to what? Go. Now you say, well, how low is low? If it's smaller than the level of significance. So that p-value is a probability that your null hypothesis is valid. If it is low, not likely, it's not likely to be valid. That means you automatically do what? Accept the alternate, because the null has to what? Go. If the null goes, the alternate is valid. So this hypothesis testing comes down to one thing, that p-value. It's a probability your null hypothesis is valid. If it's smaller than 5%, it has to go. If it's smaller than 1%, it has to go. If it's smaller than 10%, which is not a very sensitive test, it has to go. This is all based on if p is less than what? The level of significance. So remember that statement. P is the probability that your null hypothesis is valid. If it's not likely, less than 5%, or just less than the level of significance, then it has to go. The alternate automatically is accepted. And that's what, this really means. And so, what I have here is the technical notes, which is, the alternate hypothesis H1 may or may not be the claim. That's not what we're looking for. But, we're going to relate it to the claim, as you guys have seen with all these examples, okay? So this is the modern method. It goes back to this p-value method. Now, you could read some of these notes here, because you have these technical things called the errors, type 1 error, type 2 error. But if I go back to all the examples that we already did, and that's why I circled them, okay? You see the last example here? What was that p-value? Well, it says it's equal to 0. It's not equal to 0, ladies and gentlemen. It's just that the calculator is not so accurate enough. Remember all those scientific notation answers we got? Super small? That means it was so small, that they can't even put it in scientific notation. So they say p equals 0. Well, you know what? This means p is what? What does that mean? P was less than, what's the level of significance again? 1%? Well, in this case, see this here? Yeah. So what you're checking to see is really this. Is P smaller than alpha? They're defining that threshold value to be your alpha, level of significance. That's your threshold, really. So a lot of questions are 5%. But some questions are even rarer in terms of a threshold. 1%, this example. So you say, how do I know? Because they told you right here, 1%. So what you found, ladies and gentlemen, is that the p-value of being 0, this is the criteria. P was less than alpha, okay? Because 0 is smaller than what? 0.01. Okay. There's your alpha. And the p-value right here that we got is smaller than 0.01. So the p-value is low. How low? Less than alpha. If the p-value is low, what did we just say about the null? The null has got to what? Go. And the null did go. So I just want you to verify that the traditional method and the modern method, p-value method, will give you the same conclusion. It's not going to give you a different conclusion. It just makes things a little bit easier in some ways. It's almost like you don't have to create a decision rule. So if the p-value is low, the null has got to go. And that's the phrase we use. The p-value is low, the null has to what? Go. The p-value is low, the null has to go. How low does the p-value have to be low, smaller than alpha? So I'm going to verify Remember how we've been doing this? Look how low this p-value is. Is that a small p-value? Don't tell me that is what? 6. No, because this is e to the what? -40, ladies and gentlemen. So what this is saying is that your p-value is less than, what was alpha? 5% here. Alpha is right here. It's 5%. So since the p-value is less than alpha, 5%. The p-value is low, then what has to go? The null has to go. So guess what? No. The null did go. Didn't we cross out the null? Yes. So the p-value is low, less than alpha, the null has to go. What about this? You guys know what the p-value is here? I'm going to write it down. Your p-value here, and this is approximate. How many zeros if it's scientific notation? 1, 2, 3 zeros, and that's going to be a 5. Okay? This is that p-value here. So if the p-value is low, how low does it have to be? Less than alpha. What's alpha here again? 1%. So ladies and gentlemen, yes, 0.000, was it 3 zeros and a 5? Is smaller than 0.01. So you got the p-value less than the what? Alpha, level of significance. Whatever, it doesn't write. Okay. So p is less than alpha here. The p-value is low, then the null has to go. And sure enough, didn't the null go? Yes. Okay. Let's look at the prior example. What is this example here? What's our alpha? Alpha's 10% here. Is that right? And then what's this p-value? What are you guys seeing here? Is 0.377 less than the alpha? Okay, here's the p-value. P-value, we already got it. Alpha, 10%. Is the p-value less than alpha? Say no. Say no. This is the p-value is not less than what? Alpha. The p-value is not low. What do you think your conclusion then is? You have to accept the null. The null doesn't go. Okay? We can't say that the p-value is low because it is bigger than the threshold of 10%. So notice this. Didn't we accept the null here? Is that true? Did you guys notice that? All right, pretty good. Let's try another example, but let's use the p-value. Notice, what's the benefit of the p-value? Right? The p-value method. You guys know what the benefit is? There's no what? Decision rule. This is the benefit of the modern method. Let's give you an example. The mean. What do you guys care about in terms of mean? You guys like pets? You know what I noticed the other day? And speaking of a pet, I was walking out. I was looking up. And I seen a whole bunch of green birds. They look like green tropical birds. Has anybody ever noticed green tropical birds? Do you see them some last night? And they're really loud? Yeah. Do you remember ever seeing them before? I don't remember seeing green tropical birds in LA. I got to look this up. Should we ask ChatGPT? Green tropical birds in LA? First time I ever noticed them. Anybody else know what I'm talking about? And they're loud? Are they really? Do you guys know what kind of birds they are? I don't either. Huh? They're really big, aren't they? I wonder what they eat. Other birds? Huh? Mole? Yeah, I have to go. People have been asking me, my birthday's coming up. It's not. My birthday's kind of coming up. People ask me, what do I want to do, right? For my birthday. And my favorite restaurant kind of closed. Well, it's kind of one of my favorite. I have a lot. My favorite restaurant. It's called Taps. Taps in Brea. Taps like Fish House in Brea. Closed after I don't know, 25 years or something. You guys ever eaten at Taps? Anybody here hear of Taps? It's actually a brewery, Taps Brewery. Anyway, really good food. Really good beer. Great beer, great food. Inexpensive beer, even. Like you could go get a case, and it wasn't a lot of money. You're like, oh my God, they brewed their own beer, and it was really good. So sometimes when I'd have parties, I'd go over to Taps. I get a whole bunch of beer from Taps. It wasn't that expensive, but it was really good. All the way in Brea. So I can't go to Taps. Maybe I'll have to go to that mole place. What do you think? I'm going to have to try it out. Maybe I'll go. You know what I'm going to do? I'm going to go by myself. Are they really? Maybe I'll just go by myself. And I'll recon it. I'll say, I'm going to go see what's going on here. Go by myself, and then I'll try it out. Some good mole. Actually, that's what I was thinking of going for my birthday. My birthday? Since you insist. If I tell you, I have to have a present. I'm just joking. I don't need a present. An A is your present to me. Oh, okay, it's a present. My birthday is October 4th. So my wife's saying, hey, what do you want to go to eat at your birthday? I'm like, well, I can't even decide what to do tomorrow, and you're asking me about my birthday. I don't know. I can't go to Taps. I was thinking, is there any good places in LA? And I keep thinking of that mole place. I tried going to this place down the street, and it was closed. It's like Thea's Mole or something. Mole Thea? I don't know. Thea something? Thea Mole? Down the street? It's closed. I can't even look it up on the internet. Yeah, maybe I should go by myself. Think my wife will get mad at me if I go by myself? Yeah. She'll get mad. She gets mad at me for everything. She argues with me about everything. I finally told her yesterday because we went to the movies. And she got a ice cream. So I got a Dr. Pepper She got an ice cream. Then she asked me, should I get the Snickers ice cream or should I get this other drumstick ice cream? I already know it's a trap. So why you ask? If I tell you what you should get, you're just going to argue with me and disagree and say I'm getting the other one. And I'm not even going to eat the ice cream. You are. You should know. She just started laughing because she knows it's true. So if I say get the drumstick, no, I'm getting the Snickers. It's like, why'd you ask me? And I'm not even eating the ice cream. So I know she'll get mad if I go have the mullet. Why'd you go without me to get the mullet? I want to see if it was good. If it was really good, I'll take you. If it's not, I won't. I'm looking now. I only take you. Oh, that's a good one. Thank you. I'll say it in my romantic voice, right? You know, I only take you to good places. I can't take you anywhere else. What the hell? I gotta know if it's good if you're gonna be there. She'll hit me anyway. Yeah, I was just trying to think. Wow, what's it good? It's in the back of my head, that mullet place. Darn it. But LA is like, whoa, man, there's not a lot of great places in LA. But I got to try that place. There was a really good place. You guys probably don't know, or maybe you do, but there was a place in Boyle Heights that was phenomenal. See if I can remember because I didn't have very much coffee. Ah, yes, Serenatas, Boyle Heights. Really good. I'm talking amazingly good. It was like a gourmet Mexican food. Gourmet. They don't have like a chorizo plate there. You know what I mean? Everything is like gourmet. You even have the beans and you're like, oh my God, what did they just do to these beans? I think they put cream in them. They did something. I never was figure out what they did. Everything was phenomenal there at this restaurant. You know, it's a kind of restaurant where I think you guys know who Barbra Streisand? I heard Barbra Streisand used to go there. Boyle Heights, she'd go there. A lot of times I go there and you'd run into like actors and actresses. You know, they eat at Serenatas in Boyle Heights. You know how you get, and they had valet parking in Boyle Heights. And you know how you got to the parking? Through the alley. You had to drive through an alley to get to the valet parking, and everybody you took are like, where are you taking me? They looked at you like, what's going on? They're going to jump out of the car. But you say, no. You gotta get to the valet parking through the alley. They never believed you, but then sure enough, you drive through the alley in Boyle Heights, and this guy jumps out, you know, and get your car, and you eat at Serenata. That's a very good place. That the owner passed away, and so that kind of what happens sometimes. The owner passes away, and I guess the owner cares so much about the restaurant, doesn't close it, and the family doesn't know what to do with the restaurant. So that's what happened in this case. But it was a phenomenal food there. It's just, oh my God. Everybody who I used to take people there all the time. So it's like, you can't go to Serenatas. You can't go to Taps. Man, I don't know where to go. Maybe go to that mullet place. Should I go today for lunch? What do you guys think? Then my wife's going to be, where'd you go? Why'd you go? Why didn't you take me? I should go right now. Let you guys watch some math videos. I'll go now. They open now for breakfast? Could you have mullet for breakfast? Why not? I might have to go to San Diego just to. Yeah, I'll tell you. You know what I'm going to do for my birthday? I'm going to San Diego. I'll eat at my favorite places down there. Cafe Coyote, San Diego. That's a good place. I might do that. But I don't know. I'm gonna check that out. I'm gonna think about that. See, should I go out there? Let's get the p-value method. How about, can we create an example around food? How expensive is this place? I think it's worth it too. I went to, do you guys know down the street, what is that place? I'm going to mispronounce it. I forget what it even means. La Cayeta? Anybody been there? It's supposed to be a pretty, it is a good place, but it's good. A lot of people go there. A lot of politicians go there. It's down the street, next to the bakery. Javier's? I've heard of that. I haven't. Yeah, you had a beer from there? Do they brew their own beer? I've heard of Javier's, yes. I've never tried it. I've heard of it. People have said, oh, it's good. I'm not sure. But now you're making me think, because there's one in Irvine, I think. Oh, let me think about that. Let's see, where do I go to Irvine and get? They have a good Cuban place out there. Irvine. It's next to Javier's. There's another place I go there. I'm trying to remember where I go. Anyway. The mean lunch bill is no more than $25. This is for a single person. Sorry. At where? Javier's. As claimed by who? Should we say Snodgrass? Danielle, yeah. I was gonna name my daughter her middle name Danielle. I should have. A sample of 300 lunch bills. Reveal a mean of, still down. How about this? A mean of what? $28.32 with a standard deviation of $3.75. Use the 5% level of significance to test this claim. Okay. So you say, what parameter are we talking about? The mean lunch bill is what? No more than what? $25. Now, Javier's. As claimed. This is a claim. Okay. So, no more than. So, I'm going to have to know the meaning of no more than. Do you guys remember the meaning of that? Let's write it down. What is no more than? Isn't that less than or equal? Isn't that less than or equal to? So where does this belong? Do you guys know? Is that a null or is that an alternate? Where does it go? It's a null. Good. What's the logical opposite of this? It's greater than what? 25. Yeah. So automatically, I look at this and I think, you know what? This would be, if I use the traditional method, if I did, this is a right tail test. Is that true? So you might say, by the traditional method, this is a right tail test, just to let you guys know, but I'm not going to draw a bow because I'm going to use the what? The p-value method. So, okay. So the p-value method, what does it require us? We have to know the what? 5% level of what? Significance to test this claim. So by the p-value method, we need to know, is the p-value greater than alpha? Or sorry, less than, yeah. Smaller than alpha. Is that p-value low? So let's get the sample information. We're still going to need a sample size. We're still going to need a sample mean and a sample what? Standard deviation. So let's read. It says a sample of what? 300 bills has a mean of 28.32 with a standard deviation of 3.75. So here's my n. This is the sample mean. This is the sample standard deviation. 300. Sample mean is 28.32. Sample standard deviation is 3.75. I still need the mu naught, the mean and the null hypothesis. It's 25. Z what? Test. Okay. So I have to check to see if that p-value is less than 5%. Is that p-value less than 0.05? Okay, let's get out the TI. So, okay, TI. Stat. Test. Z-test. Mu naught is 25. What's the standard deviation? 3.75. What's the sample mean? 28.32. Okay. And then sample. What is this? Sample size is what? 300. I still need to know. Is it a right tail test? Okay, it's a right tail test. Okay, let's calculate. What's that p-value, ladies and gentlemen? So P equals 2.367 to the nearest thousandths. And then you have this e to the minus 53. Do you guys remember that? What is this portion again here? This is scientific notation. Is that right? You know what that means? There's like 52 zeros before the 2. That's a lot of zeros. This means P is approximately what? 0. If P is low, how low? Well, that 0 is smaller than what? The level of significance of alpha. This is my level of significance. This is alpha. So if the P is low, the null has to what? Go. Your null goes. So, okay, null, where are you? And we got lazy. We didn't label the claim. Okay? So the null has to go. The null has to go. It happens to be the claim. Is that true? So what does that mean? If the null goes, we accept the alternate that the mean bill is greater than $25. So the sample what? Does not support the claim. So there it is. Sample does not support the claim, ladies and gentlemen. Because the p-value is low, the null has to go. Time for a what? Break. All right, we'll give you guys a break. We'll see you guys in a few minutes. All right, ladies and gentlemen, let's take a look here at what we'll be doing, which is the same thing. So we're going to look at hypothesis testing about a mean mu still. You go still, but this time you're going to have to take a what? Small sample. And you say, what's a small sample? Anything under what? It's like no more than less than or equal to 30, I believe. Okay. So this is what's considered a small what? Sample. Now, I just want to give you guys a couple of notes here. If the sample is small, here's going to be a summary. In the TI, instead of using the z-test, which is based on the normal distribution, the standard normal distribution, we don't use that in the TI. What you'll use is the t-test because you're going to use the student's distribution. Okay, to let you guys know when you have a small sample, anything under 30, you're going to use the t-test. Okay, just to kind of paraphrase or give you guys the notes of what you need. It's going to be a t-test, student test. And your critical values, since you're using that t-test, okay, for the critical values, you don't use inverse norm. You say, oh, I had inverse norm to get those. Nope, that was based on the z values. So for your critical values, you're going to use what's called inverse t. Okay? So just to kind of summarize some of this again, critical values is based on the TI on the inverse t function, and then you have something called a definition of what's called a degree of freedom. So I'm going to put these notes here. Your degree of freedom, this is the definition, abbreviated DF, is simply one less than the sample size. Okay? So you do have a definition, degree of freedom, right here. It's one less than the sample size. Now, this is what you work with in the TI. And again, that's when you do a hypothesis test about a mean and your sample is small, under what, 30 data values. So that's what we're going to work with. Small samples now. Since our internet is down, still down. I don't know why it takes so long to get the internet back up. You know. But anyway, this is what we're going to be working with. You got inverse t, degree of freedom. You're going to need to know what that is. This is all information on the TI. So let me change that color. T-test, okay. You got all the relevant information. It's still hypothesis testing about a mean, though, but now it's a small sample. So let's give you guys some examples, okay? And it's going to be a small sample. So if they say again, let's say the mean lifespan of California residents, I'll say, is 82.5 years as claimed by what organization is associated with health? I don't know.
CDC.
What is it? Okay, I'll say by the CDC. Okay, Center for Disease Control. And then I'm going to say a sample of 22 California residents reveal a mean of 80.6 years with a standard deviation of 9.2 years. Use the 1% level of significance to test this claim. So what I'm going to go over now is, again, hypothesis testing questions about a mean, but this time for what? Small samples, under 30. Okay, so under 30. And in the TI, you're going to use what's called the t-test. And when you get your critical values, you need what's called the inverse t, not the inverse norm, right? And if you're going to do that, you need what's called a degree of freedom. So we're going to go over this. And yes, online, I do have that information in the notes. You know, this is the T student distribution you use for small samples, right? Same thing for estimation. Small, you know, if you said for estimation, you had confidence intervals using that T students distribution. Same thing. But this time it's going to be what? See, this is our inverse T, you know. And we'll go over a little bit of details, but the stuff online is based on these notes, and I'm going to give you some different kind of perspective, okay? So that's the idea, give you guys a different perspective in terms of hypothesis testing, grading in my own kind of way, kind of something that students actually prefer, in all honesty. They prefer my language. Because you say, why do they prefer your language? Because that's what your lecture is in. Then you put the homework in that language, and then you put the same, you know, your test in that language. So there's some continuity there. But anyway, let's go through this, and we'll just see the differences, right? So again, the parameters are going to be about a mean. This time it's the lifespan of California residents. And then they're saying is what? 82.5 years. And again, this is a claim by the CDC. So you translate this. Mu is what? 82.5. And then this here is going to be the what? Claim. Make sure we write that down. That's the claim. So where does this claim go, ladies and gentlemen? Is that a null hypothesis or is that an alternate hypothesis? Anybody know? Where does that go? That's a null because that's a condition of equality. Is that right? Okay, condition of equality. So what's the opposite of this statement? Mu is not equal to 82.5. All right, you guys okay with that? So this is what we're setting up, and then I want to remind people they're going to use the what? %, level of significance to test the claim. So when you look at this, what kind of tail test is this going to be? It's two tails. You say, okay, this is a two-tail test. So let's set that up. Now remember, the distribution you're looking at is not a Z distribution. It's a what? T distribution. This is called the student's distribution. Student's distribution is used to approximate the Z distribution for large samples. I'm sorry, small samples. So Z is approximating T, just to let people know about this. Sorry, I said it backwards. T is approximating Z. So you have a region, do not reject the null, and then this region over here is going to be the what? Reject the null, and over here you what? Reject the null. Okay. So all of this information, and let's recall, if alpha is 1%, which is 0.01, how much is in each tail? That's half of 0.01, so that's 0.005. You guys okay with that? So I want to let you guys know alpha being 1% means half is in each tail, because there's 2. Now, because the sample's small again, and you say, well, how do we know the sample's small? Well, they say a sample of what? 22 California residents reveals a mean of 80.6 with a standard deviation of 9.2. So that sample size, sample mean, sample standard deviation. So the sample information is there, and I'm going to write it down because since I'm on the topic, sample size is 22. Sample mean, they said 80.6. Standard deviation is 9.2. Okay. So remember this. For the t distribution in that ti, how do I get my critical values? Not inverse norm, inverse t. We have a small what? Sample, inverse t. So for inverse t, you also need a degree of freedom, which is 22 minus 1. It is 1 less than the sample size. So my degree of freedom is defined to be, okay, 1 less than the sample size. So here it is. Degree of freedom is 21. Now you're going to see why we need that, okay? So you say, why do we need that? Well, in the TI, we go second distribution. Inverse T now is number 4. Now take a close look. This is different than inverse Z. Inverse T, notice they don't tell you left tail, right tail, or center, do they? So in my notes, if we go back, the notes I put for people online for inverse T now, is this the small sample? Let's see how we work with inverse T. Inverse T, we enter area to the left of the rightmost critical value. Area to the left of the what? Of the rightmost critical value. Let's see what that means. No internet connection. Okay. Area to the left of the rightmost critical value. So, what does that mean? Isn't that the rightmost critical value? You have to know your right and your left. So, let's get the purple up. That's a critical value. There's a right critical value and a left critical value. So if alpha is 1%, could you guys tell me what percent is area to the left of that? Isn't that 99.5%? So let me share with you guys how to do that. That's what it looks like to me. So if we go to the TI. Okay, 0.995. What's the degree of freedom? 21. Let's paste it. What do you think it gives us? 2 point. That's a isn't that a positive? So positive numbers are to the right. 2.83 what? 1. So you just found that right critical value. By symmetry, what's the other critical value? Yeah.
Could you have also put the 0, 0, 5?
Yeah, take a look. Yeah, I mean, if some of you guys have the default and you're used to using the default, right? You can go, but what if I did this? Second distribution inverse t. 0.005. Right? You're using the default area to the left of that left most critical value. Even if you did that, you got a negative. So this time you're getting the left and you're using symmetry. So the answer to your question is yes, you could have done that too. So those are your critical values. Now, this is the only thing that's new is for the small sample. You still have this value. What do we call that value? And this your mu naught, 82.5. So your mu naught here is going to equal 82.5. So all of this goes in your TI now. So, all right, let's get this here. So remember, you're going to use what? T now what? T-test, because it's a small sample. So small sample T, large sample what? Z. Large sample Z-test, small sample T-test. Stat. Test. T-test is 2. .5 or mu naught. The sample mean was 80.6. Sample standard deviation here is 9.2. Sample size, this is N. N is 22. What kind of test was this? Wasn't this a two-tail test? Right? Isn't that a two-tail test? Go back and double check. All right, let's see what the TI says now. Enter. Okay. What is your T value here, ladies and gentlemen, approximately? That's the test statistic as a T value. It's negative 0.9 what? 69. I'm going to get the P value as well. What's this P value equal to? 0.34 what? 4. Okay. All right. So I have the test statistic value and I have the P value here. That T is the test statistic because it's a T distribution. The P is a P value. So I'm going to write these things down. And notice what this means here. So a T value of our test statistic of a negative 0.969, that's like negative 1. So I want you guys to know that's kind of like over here, okay? Test statistic value. Negative 969. It's to the left of 0. So what I can notice about all of this is that the test statistic is where? It's in the not reject the null. That test statistic is in the not reject the null location. Notice this as well. is the p-value smaller than your level of significance of 1%? Right? This is not happening. So the p-value is not low. If the p-value is not low, you automatically accept the what? The null or the alternate? Do you guys remember? What do you automatically accept? If the p-value is low, the null has to go. But if it's not low, it's the opposite. The null stays. So you accept the what? Null. Is that consistent with the classical method of not rejecting the null? The answer is yes. So double check by both p-value, we do not reject the null, and the modern method, traditional method, do not reject the null. So you embrace the null. By the p-value method, it's the same conclusion. So you're not going to get opposite conclusions in terms of the null. Okay, you guys okay with that? Do not reject the null, so you accept the null. That happens to be the claim. Is that right? So what do we say about the sample? Sample supports the claim. Yes. So your sample is going to support the claim. $82.5. So I just want you guys to notice that both methods apply here. This is how you handle a small what? Sample. What do you guys think? Is that easy peasy lemon squeezy? How you handle small samples? It's no different other than to say what? Inverse T now. Inverse T to get your critical values. And then the hypothesis test is now going to be the what? This T test right here. Small sample. Let's give you guys another example here. Here's your example. We're going to say the mean. Oh, what do you guys care about again? The mean what? The mean number of movies college students watch on Netflix. Do you guys watch movies on Netflix? Is not 5 per week. Let's change that to 7. Is not 7 per week. As claimed by who? We'll say Snodgrass again. A sample of 15 college students. What do those college students do? Reveal what's good on Netflix? Anybody watch Netflix? What's good? So I can know what to watch? Okay. What do you guys think? Do college students watch a lot of Netflix? If they say 7 per week, that's like a movie per day. Do you guys watch a movie per day? You watch 7 on Saturday, which means 7 per week. There you go. What do you watch? That's good. I'll tell you what I'm kind of interested right now. I'm interested in watching about Bigfoot. I'm watching like I don't know what this, the Alaskan Bigfoot. I don't even live in the mountains. I think I'm going to believe now because I'm watching this stuff. I don't know. Let's say 5.6 movies per week with a standard deviation of, what should the standard deviation be, maybe? Let's say 2.2 movies. Use the 10% level of significance to test this what? Claim. Should we have you guys try it just for fun? Maybe have you guys try it? Have you guys try this one. See what you guys get. The mean number of movies college students watch on Netflix is what? Is not what? 7 per week. 7 per week. It's a mean and an interval there. As claimed, so it's a hypothesis by good old Snodgrass. All right, so what do we know? Mu is not equal to 7, is that right? So we write this down. The mean is not 7. So as we set up our hypotheses, where does that belong? Is that a null or an alternate? Good, so we're going to put it in the alternate. What's the opposite of the statement? Mu equals 7. So also make sure you put the word claim next to it. Okay? Because otherwise we're not going to know what the real conclusion of all of this is. All right, you guys okay with that? So it has the word claim next to it. All right. All right. All right. Okay, so, all right. So let's see. Okay, so how many tails is this test? This is a 2-tail test. Is that right? Say 2-tail test. Okay. So as we start to set up our decision rule, I'm going to draw 2 tails. We say do not reject the null, and over here, the 2 tails, we reject the null. This is a t-distribution. These are examples over small sample sizes. So, sample of what? 15. That's small. College students reveal a mean of 5.6 movies with a standard deviation of 2.2 movies. And again, you're using the 10% low significance. So what's the best movie platform? I'm just kind of curious. What do you guys, what's your favorite? Is Netflix the best one? What do you guys think? Huh? HBO Max? Hulu? Oh, we got to take a survey, huh? Disney Channel? Anybody? Disney? So Netflix is not the most popular? Just kind of curious, how many people prefer Netflix? Raise your hand, high and proud. Nobody? Nobody likes Netflix? Okay, we're the Hulu people. All right, Hulu. We got about 4 or 5. Okay. What's the other one? HBO Max? Oh, we got 1, 2, about HBO Max maybe. Is there anything else? Oh, what about Amazon Prime? How many people like Amazon Prime? Oh, you guys like Amazon Prime better. Okay. How many of you guys have all those channels? If you have all those channels, how many of you guys actually watch those channels? I don't. I have these channels. I don't even watch them. It's sad. 2.2. You know The Nun 2 is coming out. You guys know that, right? The Nun 2 is coming out. You know what else is coming out? Exorcist something. I forget which one it is. Is it Exorcist Forever? It's kind of a weird title. Exorcist Forever. And then what else is coming? The Queen Mary, the haunted Queen Mary is coming too, evidently. Did you guys know that? Yeah, I sent this the Nun 2 preview to my brother in a group chat text. And then he responded with the Queen Mary movie. It's like, what? They're gonna have one the Queen Mary, really? Weird. 10% level. Yeah, my daughter wants to go watch it with me, The Nun 2. That's what Ashley wants to do. You guys go to the movies with your dad? Anybody here, you go to the movies with your dad? It's okay to admit it.
Only if it's like a movie we both want to see.
Good. I don't see what's wrong with going to the movies with your dad. How about any of you girls go to the movies with your dad? Oh, there you go. Good. Ash. Not now? Oh. Well, Ashley wants to take me to see The Nun too. I said, okay, Ashley, I'll go with you. I said, good. So I guess I'm lucky. Daughter goes with her daddy. Still. I don't think Melinda doesn't want to go. She doesn't want to be with me now. I don't see her when she's older changing. Melinda doesn't want to do anything with her dad. Isn't that weird? They're opposites. One's sane and one's crazy. Does that happen with kids? One's sane, one's crazy? Well, that's what happened to me. One's nice, one's mean. All right, so we need critical values. You guys remember, how do you get your critical values? Inverse what? I got to make sure these videos never make the internet. Should you imagine Melinda watches it when she gets older? Dad, I'm the crazy one? No, that's Ashley. I'm the mean one? No, that's Ashley. No. Second distribution, inverse T, small sample. All right, now remember, this is kind of the one that's pretty tough, right? Actually, it doesn't really matter for a two-tailed test. I don't know. So how do you guys want to do it? If we go strictly with the protocol, I guess that's 95%. Is that right? If I go with the strict protocol of, okay, area to the what, left or the right most critical value? Area to the left of the right most critical value? That's the right most critical value, and that's area to the left. So if 5% is in that right tail, what they're saying is this has to be what? 95%. So, all right, TI. 0.95. Oh, yeah, we did already that. So we got to delete. Okay, what's the degree of freedom, ladies and gentlemen? 14. Okay, how come you guys know it's 14? How do you know? It's one less than the sample size. Is that right? So over here, 15 minus 1 will be 14. So good. So now let's paste this. And so that's a positive 1.761. So that's over here, 1.761. Okay, you guys okay with that? Now, because of symmetry, what about this other side? It's negative what? All right, you guys okay with those two? All right, now remember what I'm going to have to do. That's inverse t. I'm going to need this here. Mu naught is 7. So I'm going to need mu naught again because we get to use t what? Test. So stat test number 2. T-test, go down here. What is that mu naught going to be? 7. What's the standard deviation? 5.6. What's the standard deviation? 2.2. And I think this was two-tailed test. Right? Oh, sample size 15. And then two-tailed test. Yes, make sure it's on not equal. Let's calculate. So I'm going to write down the test statistic and the p-value. So t is approximately negative 2.465. Is that right? And the p-value to the thousands is 0.27027. All right. Test statistic. P-value. Remember, alpha is 10%. So negative 2.465, is that past the critical value? The answer is yes. Test statistic. So what does it say? Negative 2 blah, 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 right? You're in the reject the what? Reject the null. Is that true? So what happens when you reject the null? Say goodbye, null. You are rejected. But if you reject the null, you are embracing the what? Yeah, you're rejecting the null, embracing the alternate, which happens to be your claim. So what you're going to say is the sample supports the claim. All right, the sample supports the claim. Now, let's be careful here. Let's go verify. Is the p-value less than the level of significance? Is the p-value small? Well, is 0.027 less than 10%? The answer is yes. So if the p-value is low, the null has to go. And the null did go because the p-value is low. P-value is low, the null has to go. So the p-value is smaller than the level of significance. So by either test, so you guys know, it's a consistent process. So, you might take classes where they start talking about the p-value, smaller than the level of significance. You think, oh, p-value is low, the null has to go. But that has nothing to do with the claim. You got to go back and see where you left the claim. If the claim is in the null position, then you got rid of the claim. If the claim is in the alternate position, then you accepted the claim. So remember, there's two issues here. There's the technical issue, and then there's the issue of where the claim has to be. And you always have to write that down. That's why I put it in red. Write it down because you can't do it without it. You might, I've taught this for years, and people, will get so confused by it. That's why I always put the claim there, because you have to go back and double check what does it mean about your claim. Now, let's ask you guys these questions here. Where are the people that like to have pets? Should we have pets or should we have children? Should we ask you a children question or pets? A pet question. All right. So I'm going to say this here. What is the following data represents the number of pets college students own. All right, so if we're going to take a sample here. How many pets do you have at home? One. How many pets? One. How many pets? How many? One. How many pets? 6 pets. How many pets? 4. How many pets? 1. How many pets? 0. How many pets? 1. How many pets? How many? 7. How many pets? 0. Okay, good. Okay, I just gathered data. As you guys know, it's a bad way to do it because I did it based on what? Convenience. Whoever was closest to me, bad. You want your samples to be random. If not, systemic. Okay. Following data represents the number of pets college students own. Well, I guess I can say it this way. I'm going to do it this way. College students own less than 4 pets as claimed by Snodgrass again. Okay? Use the 5% level of significance to test this what? Claim. Now, what do you guys notice about this example here? How is this example different than all the other ones you just did? They gave you a list of sample data values, didn't they? So how many data did they give us? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data values. Hey, isn't that small? So n is 10. Your degree of freedom will be 10 minus 1, which is 9. The point is, isn't that a small sample? Right? You guys okay with that? So when you go through the process now, and then something else, I didn't even say a parameter. I just left it as college students own less than 4 pets. Like if it was a headline, hey, college students own less than 4 pets. Well, let me ask you guys a question here. What do they really mean? They have to be talking about a mean here, okay? And then sometimes language is done that way. They don't say the parameter, but they're referring to the number of. That's a mean. And the phrase less than 4, and this is a claim. So you might say, okay, that's mu, and they don't always tell you, but that's mu less than 4. This here is the claim here. Okay, so they might not give you that parameter. It's a number of claims, so that's a mean. H naught, H1. Where does this go? Is that a null or is that an alternate? Alternate, good. What's the logical opposite? Good, okay. All right, ladies and gentlemen, here's the deal. What kind of test is this? Is this a, what is this? Left tail test. Yes. Okay, so it's a left tail test. So we're going to label this again. Do not reject the null. And then this is going to be reject the null. This is a small sample. It's a t-test. And our level of significance, again, is going to be 5%. So what do you guys use? Inverse t, is that right? So, okay. Inverse t. There's 5%. What's our degree of freedom again? Wasn't it 9? Because there was 10 data values, so the degree of freedom is 9. Always one less there for this situation. All right. So what's this critical value? Negative 1.83 what? 3. Is that true? And then that should make some sense. How come this makes sense? Because isn't a negative number to the left of 0? So that makes a lot of sense. All right, but who can tell me what is the other piece of information you guys need? You need the mean and the standard deviation. So how do you guys get it? Exactly. You're going to have to get it in your TI. Good. So you're going to go to stat, edit. I'm going to have to clear out my list and enter my 10 data values. Right? We're going to have to get the mean and standard deviation. So 1. Wasn't there 3 ones? 6. 4. 1. 0. 1. 7 and what? 0. Are there 10 data values there? Then what do you guys do? Do you guys remember? Stat, calc, one variable stats. It's in L1 and calculate. So ladies and gentlemen, there you go. You got the sample information there. Is that true? So we can write all that down now. So the sample size should be, what is n there? Isn't it 10? What's the sample mean? Isn't it 2.2? What's the sample standard deviation? We'll go out to the thousands. 2.5 to, it's actually 530. So ladies and gentlemen, yes, when they give you a list of data, you have to go that route. Okay, does that make some sense? Don't forget, I'm going to get out the green highlighter. What am I looking for? Mu naught is 4. Is that true? So I have my mu naught equal to 4. So don't forget, this is a small sample. So you're going to do T what? t-test. Okay, you guys so far so good? So in the t-test, go to the TI again. You're going to go to stat test, go down to t-test, the number 2. And I want to remark, just like estimation, what do you guys know? That information, except for mu naught. Here, mu naught is 4. Okay, mu naught is 4, but what do you guys notice about the mean and standard deviation and the sample size? It's there. It's there. So it knows we're going to use L1 by default, that information. So good. And then what kind of test is this again? Left tail test. Okay. So make sure the TI is on a what? Left tail. So go to the left tail, hit enter. Then hit what? Calculate. So let's get the t value to the nearest thousandths again. That's your test statistic. And that's actually equal to what? Negative 2.25. Isn't that the test statistic? The p-value is 0.0 what? 26. So I'm going to get both pieces. Test statistic, p-value. So what do we notice about the test statistic? Where does it live on our decision rule? It's negative. It's to the left. Is it to the left of the critical value? Yes, it is. That's negative 2.25, your test statistic. So it is in the what? Reject the null region. Your test statistic is in the reject the null region. So if it's in the reject the null region, that test statistic value, what do you do to the null? You reject it. Goodbye, null. And if you're rejecting the null, what does it mean about the alternate? Right? I don't want to do that. It means you are what? Accepting the alternate. You rejected the null, you accept the alternate. So your conclusion is the sample supports the claim. Is that right? So your sample is going to support the what? The claim. Sample supports the claim, ladies and gentlemen, because you rejected the null. Is the p-value low? The 0.026 is smaller than the level of significance of 5%. 0.05. So here again, here's the p-value. And here's the alpha value. So what I'm actually saying again is that the p-value is less than alpha. 2.6% is in fact smaller than what? Than 5%. So the p-value is too what? Low. So if the p-value is too low, the null has to go. And sure enough, we did get rid of the null. P-value too low, the null has to go. How low does the p-value have to be? Smaller than the level of significance. And there it is. Easy peasy lemon squeezy. What do you guys think? Is this okay? And if you want to read again about, let's go to the browser here. So the internet looks like it's kind of back up. So, you know, you could read about that p-value again, the different errors, and then you got some examples here. Okay, hypothesis testing examples about the p-value as well. So, you know, it's there. case you guys want to see some notes, other examples. Okay, I went through examples there. So, my God, what do you guys think? Is Elon Musk going to buy my book, you think? I hope he does. Because my wife watches me work. She's, oh my God, you're always working. So I don't have to argue. I'm always working. Got some examples. Look at that. P-value examples. Anyway, so let's see. What do we have here? Yeah. Didn't we give you already? Okay, so let me go back here. Let's go over here to assignment number what? Do you guys know this is the last assignment for you guys? Assignment number 5 here. Hypothesis testing. So let's do, there we go. Isn't this the stuff we did today? All right. So, and then what is this going to be? What month are we in? Today's August, what, 14th? So what's Thursday, the 17th? June, July, August at 8 a.m. And of course, like I said, so here it's already in Canvas, but like I said, the notes that I've been referring to here, hypothesis testing about where is it at? Here, hypothesis testing about a mean large sample, mean small sample. There's the homework sheet. This is the what solutions. I think they're mixed together actually. Yeah, there might be. Let me double check. Yeah, I got both. What is this? Yeah, I got both big and small. It looks like. Anyway, solutions. But if you guys wanted to see some of the notes again, and I got a video here for the notes and the video for the what? The modern method, p-value method. You guys are welcome to look at that, okay? And so I'll let you guys go a little bit early so you guys can get started on your homework, okay? And just kind of ask your questions, see what you guys think. You know that Maui fire, right? What do you guys think? Should tourists be swimming in the ocean right now? Is that a bit insensitive? I think it depends on where the ocean is. What if it's on the far side of the island? Maybe. Certainly not where the fire occurred. I don't think anybody's doing that. It's kind of interesting. Anyway, okay, guys, we'll see you later.